All right, hello world. This is CS50 on Twitch. My name is Colton Ogden, and today I'm joined for the first time by Chad Sharp. Chad, welcome to the stream.
Thank you very much.
Thank you very much for coming on today. What are you going to talk about with us?
I'm going to talk about functional programming, or rather, I'm going to try to talk about functional programming. We'll see how it goes.
Yeah, functional programming is something a lot of people in the chat have definitely been interested in learning about. I've certainly been, you and I have had these conversations. I've certainly been very interested in learning about functional programming. It's something that students here on campus at Harvard usually learn as part of CS51, which is the follow-on course to CS50. But before we get into all of that, why don't you explain sort of how you got involved with CS50 and what you're up to these days outside of CS50?
Sure. So I'm not a Harvard student. I'm a senior at the University of Michigan. I got involved with CS50 because I took the course when I was in high school, and I found some bugs in the CS50 C library and submitted a pull request.
We don't talk about that.
Technically, it's all open, you know. So I found some bugs in the CS50 library, and I made a pull request. And then a year later, David responded to it, and then from then on, he asked if I wanted to continue working with CS50, and now, however many years later, it's like 3 years later, 4 years later, I've worked with CS50 for all during that time. So it's been a heck of a ride, you know.
What kind of tools have you been working on with CS50?
Sure. So I've now written, or at least co-written, a good portion of the tools that CS50 currently uses. So I've written a lot of check50, submit 50, let's see, help 50 now. And then there's a new tool that we just released just recently called compare 50. It's on PyPy if you want to check it out. Just a shameless plug there. It's a tool for detecting plagiarism in code. So useful for teachers to figure out if the students are plagiarizing code. I think that's a decent list. There have been some smaller projects here and there, but it's all on GitHub.
And you've so back to the functional programming side of
Sure.
things. You've done some of this as part of your studies at University of Michigan.
Yeah, so we don't have, unlike Harvard, we don't actually have a course that's required, or a course that's everyone seems to take about that relates to functional programming. But I'm sort of a hobbyist. I like a lot of functional languages, and even when I write code in imperative languages like Python or C or C++, I tend to adopt a functional style when I can, and I'll explain about why that is in a bit. But then I've also done a bit of undergraduate academic research, and the biggest research project that I've been involved in was called Alchemy, a language and compiler for homomorphic encryption made easy. Homomorphic encryption, a little bit outside the scope of this talk. It would take maybe a little bit too long to explain. But this was basically a compiler and a the small programming language that was written in Haskell. So that was sort of like that's my big external experience with it. I've done a few small projects myself.
You had that acronym sort of like at the ready. You're just like instantly.
Yeah. Well, it's a little bit of a backronym. It's a language and compiler for homomorphic encryption. That's ALCHE, and then there's the Y at the end. That's the last letter of easy, EAS capital Y. It's a bit of a backronym. Unfortunately,
it's a stretch, a little bit of a stretch.
A little bit.
Awesome. And to your point where you're just saying that certain languages outside of, or at least certain programming efforts of yours outside of necessarily something like Haskell or another functional programming language, you use a lot of the concepts that you've learned from functional programming in those environments as a result of sort of being introduced to those concepts. And I know a lot of people might be familiar, for example, I think a lot of people these days write JavaScript in a sort of pseudo-functionally way, using things like map and reduce and filter and those types of things.
There's been really a recent push in a lot of imperative languages. I mean, that includes Python, C++, notably the C++ 2011 standard. A lot of imperative languages are integrating functional components because basically they realize that there are aspects of functional programming that are, in some respects, objectively good ideas. And so you see languages like C++ introducing anonymous functions, lambdas. You see a sort of move towards using things like map, reduce, getting rid of state, favoring immutable sorts of things. And these are all the terms that we'll talk about in a little bit. But that's something that's certainly exciting to see, and it makes it easier to write more functional-ish code in other languages.
Cool. Awesome. Well, I'm very excited to start digging in. I want to shout out the people that are here in the chat. We have a bunch of people: True Kinesis, CyrilCS, Shresh26. And that name I'm actually not 100% if I recognize. I apologize if you've been in the chat before, but it seems like a new name. Bella Cures, Whipstreak, Nate, who said it's been so long since they popped in. Asley T, who changed her screen name from Nwanda to Asley T. Abi Tech, CJ LaGuardia. We have Timestone, Nafis, CJ, or I think CJ Lugor, I just said actually, SashaKhan32, and Kloppenberg, lots of regulars. And then some folks are asking if we could post notifications in the CS50 Discord, actually, every time we go live. That's a good point. Why don't we go ahead and switch over to the laptop view here so that we can see what environment we're going to be working on. So what is this environment that we're working on?
So this is CS50 Sandbox, and I think David has already done a stream related to CS50 Sandbox.
He did do a CS50 Sandbox stream, but what is it if folks are unfamiliar? What is
so it's basically an environment, sort of on-the-fly programming environment that CS50 makes publicly available. You can go to sandbox.cs50.io and then immediately spawn up an environment that is that is shell access to an Ubuntu 18.04 Linux machine with all sorts of programming environments installed, including what we need for Haskell here. You can customize it with not just a terminal and a text file editor here, but also an X window like for graphical applications and an embedded browser if you're doing web programming types of things.
Cool, cool. And this comes with Haskell embedded in it already.
Yes, it does. All the things that we need for Haskell. I'm just going to open up a file.
Test.hs being a Haskell file extension.
Correct. And I'm sure we'll be writing in there at some point soon.
ASMR Gaming may have a new name, may not have one. Quantum Disentangled say, hey, I just want to make sure that I don't incorrectly say that someone's not tuned in at all in our streams before. All right, I'm going to take it off to you. Let's see what we got going on.
Sure, yeah. So I suppose before I get into anything Haskell specific, I want to talk about a bit about like what defines functional programming, how it differs from other languages that you might be used to, and those sorts of things. And then I'll talk about how Haskell relates to functional programming and what sorts of things are interesting or different about Haskell, even outside of the functional sort of aspects. So broadly speaking, there are kind of two ways. There are kind of two broad paradigms of programming languages. Basically, a program is in some respects, it's a way of encoding a computation, a way of saying this is what I want to do. The sort of two broad paradigms are imperative and declarative. Imperative programming languages are probably any other language that you've ever used, Python, C++. It covers the sort of paradigms within imperative, like procedural, which is like C, object-oriented, like Java, those sorts of things. Basically, the idea with imperative is imperative. In the sense, in like the grammatical sense, means a command. When you are describing a computation, you're saying, I want to do this, then I want to do this, then I want to do this after that. The declarative style is you're more describing this is what this computation is, like not necessarily how to do it, but what something is. So a factorial of a number is the number, is the product of all the numbers from 1 up to it. Things like that, which we'll see in a moment. Functional programming tends to sort of lend itself to smaller functions. It tends to lend itself towards what's called immutable values. Immutable here meaning unchangeable. So if I say x equals 5, then x is defined to be 5. I can't change it later. It is constant. Similarly, excuse me, let me get a sip of water.
Sort of similar to using constant values for pretty much everything in another
Correct, yeah.
context.
So at least in Haskell, you can sort of emulate the immutability aspect by you putting const in front of everything in C++.
Right, or JavaScript now these days with ES6.
Yes, so that might sound a little bit strange. We'll see kind of how that works. Another sort of difference is that functional languages tend to favor recursion over iteration. Recursion and iteration are sort of are in general two ways of accomplishing the same task. Anything that I can write recursively, I can write iteratively, so long as I have access to a stack. And so broadly speaking, those are the sorts of things that functional programming lends itself to. Why is this like important in the modern age? So functional programming tends to, and Haskell actively disallows this. Mutating global variables, which, as we know, is bad programming practice anyway. It also the fact that functions can't have, or functions in general, you are generally. What's the word I'm looking for? You are discouraged from having functions that have side effects. So, in other words, the result of a function should be a function of its arguments. It should only depend on its arguments. This sort of thing is useful in concurrent programming, so where I have multiple threads maybe doing the same task. If anyone's ever done concurrent programming before, there is one problem that you'll run into that are things called data races, where two threads are trying to modify the same thing. This sort of thing is prohibited by the sort of functional paradigm, and so functional programming is used a lot in concurrent systems. Yeah, okay, then Haskell-specific things, the thing I wanted to talk about. So Haskell is a purely functional language. So unlike other things like Python, where you could write in an object-oriented style, you could write in a procedural style, you could write in a functional style. Python makes it a little bit more difficult than some other languages. Haskell, you really have to write in a functional style. Haskell mandates that you do so. You can write code that looks kind of imperative, but you are sort of mandated into writing a functional style. And so, as I mentioned earlier, everything is immutable, things like that. And then the other thing that's maybe a little bit different about Haskell than other languages is what's called lazy. Expressions in Haskell are lazily evaluated, and what that means is that, I take the result of some super expensive function. Maybe it goes out and calculates the factorial of 7 billion, and I assign that to the variable x. That computation doesn't run right when that assignment happens. It only runs when I actually need it. So x is sort of represents the factorial of 1,000, but until I say print out the number, the actual computation isn't executed. So that has some advantages. It means that if you never actually need a value, it never actually gets computed. On the other hand, though, it does make Haskell a little bit harder to profile in some instances, or at least it takes a little bit more finesse to profile it and get the optimum performance out of it.
Some people say really good programmers are lazy. Is there a connection?
Well, I mean, kind of, yeah. So really good programmers, you only do what you have to, so you write as little as possible, and it's sort of a similar idea. The only computations that get run are the ones that you literally have to do, which is, it allows you to, like for example, when you're writing Haskell, be a little bit more lax about, maybe I write something that does a little bit more work than is necessary, as long as I never actually have to use that work. It doesn't affect the performance.
Sure.
So that's a kind of interesting aspect of the language, and so that's when you're coming into Haskell, there's sort of these two things that you have to get used to. You have to get used to the fact that it's a different paradigm, it's functional, and you also have to get used to the fact that there's this laziness aspect to it too. Another notable aspect of Haskell is that it's statically typed. So like languages like C++, like C, everything has a type. There's nothing like Python where there's sort of this this sort of fuzziness around what types are. In Haskell, everything has an exact type, and it's a very strong type system. I can encode a lot of ideas in the type system, much more than C and C++, and I hope we'll get to that at some point in the stream, sort of describing that. And what that means is that Haskell, oftentimes, at least I've found, because it pushes you towards writing small functions, and because of these really strong type level guarantees, it tends to be the case that when I'm working on a Haskell project, if I can get it to compile, it's probably right. And that is something that I think is really powerful. That very much lends itself to writing correct code, which is one of my, I like languages that are like that. I don't want the program to compile until it's correct, ideally. And it also means, however, so some disadvantages of some statically typed languages that some might be familiar with is it requires you to write a lot. They tend to be very verbose, or at least they are oftentimes. Anyone who's ever written Java or C++, their verbosity doesn't just come from the fact that they're statically typed. That certainly doesn't help. If I want to create a new object in JavaScript, I need to write the name of the object like 3 times. That's certainly not ideal. Haskell has what's called type inference, which means that the compiler will figure out the type of an expression based on how you assign it. So if I say x equals 1 plus 1, well, the compiler knows that 1 is an int and 1 is an int, and it knows that plus can take 2 ints and return an int, and so I don't have to tell it that x is an int. It just figures it out for me.
It's kind of like JavaScript and C#, which actually somebody in the chat, funny enough, said does Chad Sharp like C#?
I've gotten that one before.
Those languages will let you kind of say, and even C++ now has auto, which allows you to it does some sort of like compile time inference, right?
Auto is a little bit, it's C++ calls it type deduction. It's a little bit weaker than type inference, because so the way that auto works in C++, I can say auto x equals 1, and it knows that 1 is an int, and so it basically replaces auto with int. The problem with that is, though, I can't do auto x and then assign X later. It needs to know, if I'm using auto, it needs to know right when I assign it what the type needs to be.
Right.
More advanced languages like Haskell or like Rust, things with more advanced type inference, can figure out the type of an expression, even based on code that occurs much later. So there aren't too many languages that have the really super strong type inference. I mean, I think Go does. I know Rust does. I know Haskell does. I'm not totally sure what other things do. I know C++ is sort of a weaker version of it.
Right. And then I think ASMR Gaming earlier said, was it ASMR Gaming who said it there? That it doesn't let them import sys, sad face, Haskell.
Yes, it's true. I don't think Haskell has a module called sys. Moreover, modules in Haskell have to be capitalized. So
okay.
you could maybe make a module called capital SYS. But import is actually the keyword that's used to import libraries, just like in Python.
Everything is just a text editing wrapper to the APU circuit plus GPU, RAM, SSD, etc. Once I realized that, everything started to flow.
That's true. It's absolutely true that ultimately everything is compiled down to machine code at some level because the machine has to execute it. I'm not sure. However, that doesn't mean that we should all be writing machine code, of course. So while nominally we could get the same result by, even not just writing machine code, but manually flipping transistors with a magnetic needle, that doesn't mean that that's sort of the level of abstraction that we want to operate at. And moreover, what these sort of higher level languages give you, I mean, even just when I'm saying higher level languages, I mean even C as a higher level language, is that I can write the same code that works on any architecture for which there exists a C compiler. So that would not be the case if I were writing an assembly or the more I guess kind of lower level machine code. I'm not sure whether it's lower level. It's just a different encoding of the same instructions usually. But
cool. Can we have a stream on C++? Ask Nifty 664. Well, think about it in the future. Oof. Definitely. Assembly is all we need. Says 4411.
I mean, if you want to write everything in assembly, more power to you. I would not want to live in that world. I don't think. But I would much rather. I like my abstractions a little bit too much to write everything in assembly. I've done it, but it's not. I've taken classes in college when that was what we had to do. It's not what I would consider fun. When to write, like, say, something that finds like the choose operator, like n choose k, when that takes 100 lines or something. I would much rather use a higher level language, I think, in my opinion. Someone asked what my thoughts are on JavaScript. So I'll say that I don't have tons of experience in web programming, so my opinions on JavaScript are not as educated as they could be. However, I'm less than impressed. I think that the sort of recently with the sort of push towards this more functional stuff, I like that sort of I like that sort of push. I like the sort of the way they're doing asynchronicity with promises and those sorts of things. I really don't. The main thing I don't like about JavaScript is it is something that I generally don't like dynamically typed languages as much as I like statically typed ones. So the fact that I can reference a field inside an object that may or may not exist, and it's just undefined, instead of that being some sort of either an exception, as it would be in Python, or or statically preventable. I would rather not program in JavaScript if at all possible. Although I generally rather avoid web programming in general, so I'm not sure where the web programming, my disdain for web programming begins or ends, and where my disdain for JavaScript begins. So, not sure. I don't know how helpful that is, but.
Zanipack, mhuman87, BS Moody, and Xenanon, thank you very much for the follows. You can think of your life as a tensor for the Verint state, and every possible next state as next layer tensor, etc., or not, up to you. I'm not entirely sure what that means.
I'm gonna be honest. Yeah, I don't know. I know what a tensor is, but I'm not sure what the Verint state is. So. That's above my head.
Maybe they meant current state. I'm not sure.
Tensor for the current state, and every possible next state is the next tensor layer, etc. I mean, that's.
Is that a neural network? Is that what they're describing? I'm not very familiar with.
I don't think that's a neural network. But what I know of as tensor is like the linear operator. I'm not totally sure what tensor means in that context. However, that sounds very deep and philosophical. So more power to you, ASMR Gaming.
All right, cool. Well, I'm excited to see some Haskell code.
Sure. Okay, so Haskell is a compiled language, but it also has an interpreter, which is fantastic. I wish more languages were like this. I wish C++ had an interpreter. C, I've used an interpreter for C, which is kind of okay. But interpreters are really great for sort of hashing things out, and that's probably what I'm going to use more in this demo, because I can just sort of do it live without having to take the steps to compile it. The compiler for Haskell is called GHC. So we can see it's installed in the sandbox. I haven't given it any input files, so it's not going to do anything. GHCI is what we'll be using. That's the interpreter for Haskell, and we can see immediately here I can start writing. Haskell code.
Do you want to maybe command plus that a couple times just so we
yeah.
can see a little bit larger? Maybe that might be too much. Yeah, something like that.
Is that good?
So we can just read it a little bit.
I'm trying to move this up a little bit. Okay. We can't see the file anymore, but that's fine. Okay, so let's see. So the first thing is immediately, I guess the first thing to talk about is arithmetic. That's definitely something that is pretty easy to do. Nothing particularly functional
Computers
here.
are pretty good at, yeah.
Yeah, you can just enter those in like 3 plus 4, etc.
Mind blown.
Yeah, nothing crazy there.
Functional programming.
I know this is crazy. In Haskell you've got the sort of standard operators. You've got you got true and you have false, and you've got Boolean wise and all those sorts of things that you're probably used to from other languages. The one difference that people sometimes screw up with Haskell is that just some weird operator differences, if you're ever using it, is that not equals, instead of being exclamation mark equals, is, let's do one, it's slash equals. Which is a little bit weird.
Ah, interesting. Well, I guess maybe from like mathematical notation where you have a slash through the equal sign.
Yeah, probably that actually. Probably. So a lot of Haskell is very inspired by mathematics, and so it's very likely that that's the case. Let's see. There's also the other one that people will often get confused with is first of all, not like in Python. It's just written out like this.
Oh, okay.
And then the exponentiation. So most people are used to like bitwise XOR being the caret from other languages. Haskell does, which I think kind of makes more sense, but it still screws me up when I write Haskell. It's the exponentiation is just the caret operator. So that makes a little bit more sense if you're used to seeing what 2 to the power 6 looks like written out in text. But coming from other languages, I sometimes expect that to be bitwise XOR. Someone said that the main implementation was the Glasgow Haskell compiler. That's correct. That's GHC. And the GHCI is the interpreter corresponding to the Glasgow Haskell compiler. There's another implementation called like Hugs or something. I'm not totally sure. I don't really use it. But GHC is sort of just the standard one. Okay, so then I just want to get some of this basic syntax out of the way so that we can talk about some more interesting stuff in a bit. The other thing that's going to come up later are lists in Haskell, which are sort of unsurprisingly just sort of the standard square brackets notation. I can do ranges too. If I do 1.10, it'll give me the inclusive range 1 through 10. And then even I can do, if I'm remembering the syntax correctly, I'm not remembering the syntax correctly. I forget what the syntax is actually. There's some, I know what it is actually. So if you want to do, for example, every odd integer from 1 to say 11, you can do that by just specifying the first and second elements of the list. And if I do that, it figures out what the pattern should be based on that.
That's cool. Pattern inference. That's pretty fancy.
There's nothing more. I'm sure if I do like say like square numbers 1, 2, 4, ... all the way up to like 16, I'm sure it's not gonna figure out that pattern. Yeah. So it's only the very simple patterns.
Oh, is it because you put a comma there and you didn't put one on the last one?
Maybe actually, but I'll still bet. Yeah.
Okay.
The only patterns that it's going to figure out is basically specifying a step. So that's the only sort of pattern it's going to figure out.
That'd be pretty fancy to figure out a mathematical relationship.
That would be, yeah, especially since there are many possible mathematical relationships.
Yeah.
So that would be probably impossible. Okay, so with that in mind, let's look at like what functions look like, right? So functions are going to look a little bit different in Haskell than they're going to look in other languages, and they sort of lend themselves to the idea that I was talking about before that when I say something is equal to something else, I'm defining it to be that way. I'm not assigning something to a value. I'm defining something to be a certain way. So let's say
it actually seems like a lot of people, when they first get into programming, are actually confused by this idea because they expect equals to be exactly what you're describing.
Yes.
And they're not used to the fact that it's actually right to left sort of assignment or flow of information.
Yeah, you can still sort of think. You can still like operate with the mental model that it's assignment, and that's maybe you can definitely do it. But that's sort of how I think about it and how I think is a little bit more useful. One thing I will say before I go too long on is that I learned a lot of my Haskell, at least in an introductory standpoint, from a really great book called Learn You a Haskell, and I'll be shamelessly stealing several examples from that book today.
You can probably go to it too if you want to pull up the URL there.
Yeah, learnuahaskell.com, and then you can buy a hard copy of the book or read it online, which is what I did. Although I probably should support the author, and it's really just a fantastic resource for learning a lot of introductory Haskell. So I will be sort of narrating a lot of some of the examples anyway, but a lot of them will be available there if you want to I don't know, look at them later.
Awesome.
And certainly the Learn New Haskell will probably be covering things in more depth than I will. So. Okay, so let's write our first function. So let's take a function that just multiplies the value by 2, right? So we've already seen how to do arithmetic. So let's call this function, let's say double. Double might be confusing because double is a type. Let's say double me or something like that. So I'll say double me, even though I tend to write in snake case, which means variables all lowercase and underscores where spaces would be. In most other languages, in Haskell, it is 100% idiomatic. There's basically no ambiguity what the correct style is for Haskell, and that's camel case. So some people might be happy about that. I think I'm a little bit in the minority preferring snake case. But I will do the correct Haskell style here.
I prefer snake case as well.
Yeah, I think it looks more. I think it looks better. I think it looks more. It also looks more hackery, which is kind of nice.
I've actually gotten used to because I'm learning Lisp and Clojure. I'm actually used to this case.
Yeah, yep. When I mentioned to you before the stream that I took a class where we wrote in Scheme. And I got used to that too, and it's sort of sometimes I wish that the dash. Unfortunately, it's ambiguous in almost any other language because the minus sign is an infix operator indicating subtraction, so it's not clear is double dash me a function called double dash me or the double minus me.
Yeah, exactly.
So that's sort of unfortunate, but I do really like dash as a space separator more than underscore. So we got double me here, and it's going to take one argument. So I'm going to say double me x. And then I'm going to set this equal to, say, 2 times x. And there we go, I just defined my first function.
Can you, for clarity, also put parentheses around the x? Is that, has Haskell let you do that? Or is
parentheses here?
Around this one to specify that that's an argument?
No, you can't, but there's a good reason for that. Actually, well, I took it, does it actually allow it? It actually does allow it. I would recommend against doing that, though.
Okay.
Normally, does this work? Does it look? This looks much more like the function calling syntax that you're used to. I would very much recommend not doing this, though. So I'm going to go back to this. Here's the reason why: is because when you call a function in Haskell, you don't call it with parentheses like that. So when I call a function in Haskell, which I'll do right here, you literally just say the function name and then the argument that you're passing to it. This is similar to Scheme.
Okay.
So if I say double me 3, it's 6. Now, nominally. You can write it that way because the parentheses don't change anything, but that will this will stop working the way you expect it to when we start doing functions with multiple arguments. So someone asked about how about the type of the argument. That is a great question. So this goes back to the idea that I mentioned earlier with type inference. So because that Haskell knows that 2 is an int. And that x is an int, or excuse me, it knows that 2 is an int, and that multiplication can take 2 ints and return an int. I didn't have to specify the type here, but that's a really great question. How would I specify the type? So if I were writing this in just a regular Haskell thing up here, so I'll write it in the text file. Here's what I would do: I would write double me, and I would say it takes an int and returns an int, just like that. This just declares the type of double me, and then I would write it double me. X equals 2 times x.
So you're kind of writing like an interface.
Yes.
A protocol, I guess.
Correct.
Maybe more appropriate.
Yeah, like a prototype in C or something like that. This is nominally how you specify the type. Another way of specifying the type, you could do something like, say, you could tell Haskell that x is an int or something, but that's pretty unidiomatic. You won't usually see that.
So it's more common to have this separation of the type.
Yes.
Specification and the function specification?
Yes.
Okay.
And yes, definitely. Can you give an example of parentheses not working properly? Absolutely, I'll do that in a second. Here's, let's see, does double colon make it a comment? No, actually. So literally the double colon means exactly, it means this is the type of this thing. So double colon means so double me, double colon, int, arrow int means double me is of type int, arrow int. A comment in Haskell would be 2 dashes like this.
So int, arrow int is kind of like a lambda expression.
How do you mean?
Sort of. In as much as it specifies what the function... It's like a function, sort of like an abstract function specification at the type level.
Yeah. I mean, it's really... So this is equivalent to in C, int double me int, right? It's equivalent to this. It's just Haskell's different syntax for it.
Well, I mean, if you just got rid of the double me and you just looked at the int arrow
Yes.
int, that would be sort of like a lambda. Not a lambda
Correct.
in the sense that you're actually defining the behavior of the function, but just the signature of what that function is. It's on its
Yes, it looks like it does look like a lambda, but actually int arrow int is actually a type in Haskell. So this is literally what the type is called
I see,
for
okay.
function from instance. Someone asked capital int or lowercase int. In Haskell, types always are capital. The first letter is always capitalized. So in Haskell, int is capitalized.
So even if it's just a primitive type, it's everything is basically almost like everything's an object if you're looking at it from a Pythonic point of view.
Yes, yeah, from that standpoint. So types just have to be capitalized. It's something that Haskell enforces for grammar ambiguity reasons, sort of. Okay, so and a really great thing in the interpreter, this is so helpful in Haskell, is what the interpreter allows you to do is in these interpreted expressions, I can do :t. This is something that this isn't part of the Haskell language. This is just an instruction to the interpreter. And what :t does is it tells me the type of the ensuing expression. So say :t4. This type is a little bit more confusing than you're probably used to, and I'll talk about what this numt arrow t means. But the int is sort of int satisfies this constraint, and we'll maybe get to that in a second. But maybe something that's a little bit more. The type of the character C, it tells me that it's a char.
And there's a difference, I'm presuming, between this equals arrow and the dash arrow that were used up in the
and I will definitely talk about that a little bit later in the stream, what this arrow means. But basically, if you're familiar with interfaces in Java or traits in Rust, for the one of you out there that probably writes in Rust.
Right here.
Yeah, just me. Basically what this is it's or I'm supposed to be familiar with the concept of like forward iterators and reverse iterators in C++ and those sorts of things. What Haskell allows you to do is specify what are essentially interfaces. It calls them type classes. And then you can write generic functions. So I can say that this function works for any numeric type, or whether it's a float, whether it's an int, whether it's anything like that. And so Haskell sort of allows you to do the same thing. And so what this is saying is that 4 is I could interpret it as any numeric type that I give it. Someone says single quote for chars and double quote for strings like C. Yes, exactly. Double quotes are for strings. So for example, foo, something like this, is a string. If I do :t foo, you'll actually see something interesting. It won't say string. It'll say a list of chars. In Haskell, you can write string. I can write foo, and call it a string. But a string and a list of chars, they're just aliases of one another. So a string is literally defined to be a list of chars. So this thing is giving me sort of the most technical definition, which is this is a list of chars. So the same thing as a string.
It's not all that unlike C, actually.
Yeah, exactly. Then there was one thing that I did want to get back to, which is someone asked about an example of where that parentheses thing doesn't work. I mean, the thing to sort of just remember is that when calling functions in Haskell, there aren't you should not be using parentheses at all. But I'll give it a more explicit example here. So suppose I'm going to write a function with 2 arguments. I'll say double us. And I'll say it takes 2 arguments, and it returns 2 times x plus 2 times y, or something like that. So what you might be thinking is that, then can I write it like this, double us 1, 2, something like this, and it won't work, and it'll give you a sort of unintuitive error message as to why that's the case. But basically, because what I just tried to do here is I just tried to pass it a single tuple. Haskell has the notion of tuples, just like Python does, so like 1, 2. If I look at the type of this, it says that basically, again, remember this numt1 thing just means that these things are numbers of a sort of unspecified type. So this is a tuple, in fact, not just a. And so when I do double us 1, 2, what I'm trying to do here, what Haskell sees me trying to do here is call this function that takes 2 arguments with 1 argument, and passing in a tuple instead of an integer. So it just doesn't work. It tries to add, it can't multiply 2 by a tuple. There's no way to do that, which is basically what that non-intuitive error message would have told you. So how do I call this instead? Well, I do double 1 space 2, and that works.
It's interesting that the sort of the type returns a tuple with the operators or the nums reversed.
Yeah, I'm not sure. I mean, this is equivalent, of course, since it's numt and numt1. I don't know why it chose to order them that way. I don't think there's anything really special about that. It's just what the interpreter is doing when it's Someone in the chat says point free style double me equals this, and that is, you are exactly right. Another way to write this, and I'm going to cover this in more depth later, I hope, is that you could write this. That syntax looks much weirder, and it's much less intuitive initially, but it hints at something very interesting about Haskell, which actually I could go into that now. I was planning on going into it later, but I could definitely go into it now. And here's going to be my sort of motivating example, or something that may seem a little bit strange. What do we think the type of? I showed you what the type of a function that takes one int and returns one int looks like. It looks like this: int arrow int. What about something that takes two ints, right, and returns an int, something like that, like this double us function? How would I write the type of that? So remember that double us is xy is equal to 2 times x plus 2 times y. So how would I write the type of this? Well, as it turns out, this is how you'd write it in Haskell. Double us int arrow int, which seems strange, right? This seems like like if an int arrow int is a function from int to int, what is int arrow int arrow int? So there's the sort of quick and dirty way to just parse this in general for Haskell is you can just say that the last thing after the arrow is the return value, and everything before it, any things that are delimited by arrows before it, are the arguments. So I would read this as it takes two ints, it returns an int. But actually, the reason that the syntax is the way it is, the reason that it's a little bit weirder, is for something that's actually much cooler than this. And I'll explain that real quick here. So let's look at the times operator. So this is something that takes a number, right? So it's a generic function. It works for floats, it works for doubles, it works for etc. So that's what this num a is here. It's saying I can take any numeric type a, and it's a to a to a, right? So using that syntax that Cosmic Louis 92?
Cosmic Luis 92, I'm guessing.
Cosmic Luis 92 pointed out. Instead of putting the times in the middle of the two values, I can do this. That is just, instead of using times as an infix operator, I can put it beforehand like any other function as long as I put parentheses around it. But what happens if I just call it with one argument? In other languages, this would probably be a type error, right? If I try to call a function that takes two arguments with one argument, this would be an error. Now, it's telling me that it doesn't have any instance for show, which basically means the type this ends up being isn't something that's displayable by a string, but actually, wait, here's a better way of describing this. So we had times 2, 3 here. Well, I can put parentheses around this. Right, so this is sort of just like you're sort of accustomed to with associativity of like the addition operator, like 1 plus 2 in parentheses plus 3 is the same as 1 plus in parentheses 2 plus 3. It's the same sort of idea here. I'm basically evaluating times 2 first, and then I'm evaluating that on 3. Okay, what does that mean though? So let's look at just this times 2 and what the type of this is. So times 2. Not sure why I just lost the ability to type numbers.
That's weird. Buffering
okay.
error.
Apologies for that. So the type of times 2, whereas remember, so the type of times here was a to a to a. The type for times 2 is just a to a. So I've gotten rid of that first a. What does this mean here? So let me define another function and call it times 2. X equals times 2. Okay, so now x is a function. And I can call x on, say, 4, and it'll multiply 2 times 4. So what this is called, it's called partial application. So times is a function that takes two integers and returns an integer. If I give it just one integer, it sort of hard codes that integer into times. And so if I give it, so times 2 is a function that takes additional argument and multiplies it by 2. Does that sort of make sense?
So does every single function then only have one argument?
Technically, yes. So and that's exactly what this syntax here sort of implies. So really, there's implicitly kind of a parentheses around here. So what this means is double S is a function that takes an integer and returns a function from integer to integer.
Right.
So it takes x, then turns a function that takes y, and results in this.
Interesting.
So that's implicitly, it's sort of syntactic sugar, I suppose, for it. But it is completely identical. It's just as powerful as doing modeling functions as multiple arguments the way other languages do. The way other languages model functions with multiple arguments would be something like this. Say double us, and it's going to take in a pair. I'm going to call it x and y, and do 2 times x plus 2 times y. And just to make sure there aren't naming conflicts, I'm going to put a prime after this. An apostrophe, in other words, that is prime. So and in this instance, now I have to know both arguments, what both arguments of the function are going to be before I call it. So now double x 1 2, and I can pass the pair, and it does the same thing. This notion of partial application is sort of it's just as powerful as it does everything that the sort of model that other languages use, where a function that takes 2 arguments takes a pair of 2 arguments. This other sort of idea where a function that takes 2 arguments is a function that takes 1 argument and returns a function that takes 1 argument is really sort of, it's more powerful because it means that I don't have to know all the arguments that I want to evaluate the function on in order to use it. It's kind of, it's a little bit strange initially, but it's actually a really powerful feature of Haskell. I hope I did that explanation justice. It was kind of ad hoc a little bit.
It is a bit strange, yeah, because usually partial application returns a higher order function that sort of injects one of the arguments.
That is essentially the case here.
Yeah, and it's just an interesting, different way of modeling it, or at least looking at it.
Yeah, so that works for anything. So say like plus 2. This plus 2 is a function that it's going to take in. Okay, it's buffering again. I apologize. We're into a little trouble. If this gets too bad, we might just install GHDI on your laptop if it isn't already.
I might already have it, to be honest.
So plus 2 is a function that just takes an A, returns an A, or takes a numeric type, returns a numeric type. Bound function and JS are similar, maybe, says KZ Don.
That's Kareem.
That's Kareem. I recognize the username. Actually, I'm not that familiar with bound functions in JavaScript. However, I am familiar with bound functions in C++, and they are the same as that. So I imagine that it's a similar sort of idea here. Yeah, I imagine that's probably the case. Okay, so. Where do we want to go next? Let's see.
Thanks to Official Base and Beautiful Melancholy for the follows, and also a shout out to Bavik Knight for joining us. I'm still wrapping my head around the fact that all functions take 1 argument in Haskell. It's fascinating.
It's a really interesting idea, but you don't necessarily even have to know that, right? I can still use say double us, right? So which I've already defined, double us, right? Yeah. So double us. I can still use it as if it takes 2 arguments. I just do double s 1 2, but implicitly what Haskell is doing is that function application is what's called left associative in this instance, and so it's really doing that. It's saying double s 1, and that returns a function, and then it's calling that function on 2, but thanks to Haskell syntax, I can just write double s 1 2, and it results in the same thing.
So double s 1 on its own isn't really that meaningful?
Double s on its own.
Double s 1. If you were to just pass in 1 argument.
Well, it's meaningful insofar as this is just some other function. So I could say for example, and we'll talk a little bit more about higher order functions in a bit. Higher order functions here are basically just functions that take other functions as arguments. So suppose let's say for example, and I will get back to your question, but I have to introduce one thing first.
Okay.
So for those who might be familiar with functional programming, probably know a little bit something about a function called map. What map does is it takes a function and returns a function and a list, and applies that function to every value on the list and returns the list after applying that function to every element. So let's first, just to get an idea of what map is, let's look at what the type of it is. And in Haskell, if you want to figure out what a function does, the type usually encapsulates a lot of what the function is. So in this instance, what does this do? It takes a function from A to B for just generic types A and B. It takes a list of A, and then returns a list of B, right? So it sort of makes sense that for every element in the list of A, it's applying this function from A to B and giving me back this list of B. So how would I use this? Well, let's say my function is going to be plus 1, and I'm going to do 1, 2, 3, 4. Right, so what it did is it applied the function plus 1 to every element of that list.
So plus 1's a built-in function? Just shorthand for increment?
That's the thing. Plus is a built-in function. I'm just feeding it. I'm feeding it an argument initially.
Okay.
Right. So I'm turning this. So what map expects is a function of 1 argument. It takes an A, returns a B.
So this is Lisp-like actually, which is kind of cool. I like that. Yeah.
Yeah, so that's why it's super useful for these sorts of things. Map here is a higher order function since it takes a function as one of its arguments, and so this is exactly where it's useful. So I can do double s in the same way. Double s 2. What it's doing is calling the first element of this resulting list is double s 2 1. The second element is double s 2 2, double s 2 3, double s 2 4.
Okay, I see. I think I understand.
So that's map returns an iterator to be precise, not a list, which is a performance efficient with large data. So in Haskell, that's not really true. So Haskell doesn't really have the notion of an iterator. In Haskell, map does return a list, and we can see that that's literally true just based on the type of map. It is true that on, say, Python, map would return an iterator. That is true. But at least on in Haskell, it does return a list. Now, this list is lazy, right? So, in some respect, since Haskell is lazily evaluated, if I do something like say, let x equals map double s 1, 2, 1, 2, 3, 4. That computation hasn't actually executed yet. It doesn't actually execute until I ask the interpreter to print x. So even a bit of an example of that would be say I wanted to do here's an example. So remember that range syntax from before in Haskell, where I could do 1 ... 10, it'll give me all the numbers from 1 through 10. You can do the same thing with infinite lists. So if I don't specify an end, this is actually an infinite list, right? And so it will continue printing numbers here forever, as long as I let it. So this is in fact an infinite list, but of course it's not storing an infinite amount of numbers in memory. So lists in Haskell are somewhat like iterators in that respect because it's lazy. And so what that means is, so say I did map +1 again to that infinite list. Here's an example where laziness matters. So in any other language, if in any other language that is strict, this computation would take forever. Python would be an exception here because it uses iterators, and iterators are lazy. But in any other language where map is implemented like this, this would take forever because in order to figure out what x needs to be, it would need to add 1 to every integer, which is impossible. And so, however, notice that finished immediately, right? And I can even take some values from x. So there's a function called take in Haskell, which given a number and a list, gets me the first n elements of that list. So if I say take 4, it gives me the first 4 elements of that list. So I can say take 10 of x, and it'll tell me what the first 10 elements of x are, right? Which makes sense. So I added 1 to the numbers 1 through 10. But even though this x is an infinite list, Haskell has no problem representing it because of the fact that it's lazily evaluated.
That's pretty awesome, yeah. It just kind of allows you to express a relationship and then only realize it when you need to, when you care about it.
Exactly. So you could definitely do lazy evaluation is independent of functional programming. There are strict functional languages, like say OCaml or most Lisps, and nominally, you could have a lazily evaluated imperative language. That's less common. I can't think of one off the top of my head. But I would argue that laziness, and I would argue that is because laziness is like, it lends itself to functional programming in that way. Like I'm expressing what this relationship should be. I'm expressing that map should be, in this instance, the list of all natural numbers with 1 added to them. But the work only gets done when I need it to, which I think is really quite cool. Someone allows you to say, which allows you to stuff take2.map times 2. Yep, that's. I'd done this example before I saw that. So thank you to Cosmic Louis. I got Louis?
I think it's Luis.
Luis, I'm so sorry.
I think Louis is with an O.
Okay, yeah, you're probably right. Yeah, this is bad. I'm a very lazy imperative list of microcompiled code, ASMR gaming. I like it. Okay, so let's see. What else should we talk about? Immediately. We can start getting into talking about data structures, which I think might be interesting, seeing how you might implement lists. We wouldn't get the same syntactic sugar with the square brackets, but we could do that. We're implementing a tree or something like that, and that will get us towards talking about these type classes, like this num type class here, which we can talk about. Someone at ASLI_T asks, could you take 20 to .30x as in the form of the 20th value to the 30th value of x? Oh, yes. Let's see. What is the... hold on. Yes, you can. I just need to remember what the functions are to do that. Yes. So you would do... let's see. I think it's drop. So drop is a function in Haskell. I just have to remember all my prelude things. So drop, it looks exactly like take. It takes an int in a list and returns a list. The difference is instead of taking a value from the list, it drops that many elements from the front of the list. So like drop 2, 1, 2, 3, 4 should give me the list 3, 4. It just drops the first 2 elements. So basically, in order to accomplish what ASLI-T suggests there, I would drop the first 19 elements and then take the next 10. So I would say drop 19 from x. Does that give me what I want? Well, let's see. And then I would take 10 from this, something like this, right? I suppose you Take 18. Yeah, there we go.
Nice.
So this is exactly what you want. And Cosmic Luis, getting this right this time, again has expressed this in a slightly different way, which is also just fine. And this is, if I were writing it, I would have written it exactly like Cosmic Luis does. He brings up a really useful operator in Haskell, which is the dot operator. Dot, and again, how do we figure out what something does in Haskell? We ask the compiler what the type of it is, or the interpreter what the type of it is. So the dot operator here. It seems pretty complicated initially, but it isn't so bad once we look at it in a little bit more depth. So it takes a function from B to C, it takes a function from A to B, and returns a function from A to C. Or you could also alternatively say that it takes a function from B to C, function from A to B, takes an A, and gives you back a C. Basically, this is function composition, right? So this is take this first function. This works exactly like you'd expect it to in math, the sort of circle operator in math. So for example, if I had like +1 dot times 2, if I give this an argument, what it'll do is it will first do the times 2, and then feed the result of multiplying this number by 2 to the +1.
Right.
So it's just composing these two functions together, and this notion of composition is something that's very common in Haskell. So if you'll notice, basically in this last example, I was feeding the output of drop 18x to the input of take 10, right? And so I can do that sort of same idea here, where I can just compose take 10. I can compose this with drop 18. And then call the result of this whole function, this new function that I've made, on x, right? And that'll work too.
It's a very flexible language.
Yes, it allows you to write really quite concise code, which I'm a big fan of. Someone says drop while x is less than 20 on range 131 in Python with the Iterators module. Yes, that would absolutely work. I think is drop. I don't think I remember drop while being in Iterators, but you might be right. I'm definitely not an expert there. Haskell has a take while. I don't know if they have a drop while. They do actually. So they do have a drop while. You can do the same thing here. So you could do drop while, and then, again, so this takes a function from A to bool. So a function that goes from an element of this list to a boolean, which would indicate whether or not I want to drop it, and then it would take a list of A, and return the list of A after I've dropped those things. So I can do the same thing here, where I do drop while, let's say, less than 20, right? X, and then do like take 10. Something like this. So I'm using a bit of syntax that I haven't shown yet with the $sign. But yeah, so that does the same thing. Moreover, I guess I could do, instead of taking 10, I could do take while greater than 30. Take while, sorry, less than 30. Oops.
The buffering issue.
Yeah, sorry, this buffering issue.
Thanks to Jock, Meeks92, and bnugs317 for the follows as well.
Take while less than 30, or I guess less than or equal to 30. And that should work also? Yeah, so these are all sort of the same ways, different ways of doing the same thing. Briefly, you may have noticed that I introduced another operator sort of unintentionally there because I'm so used to writing it. It's somewhat annoying to have to write parentheses around drop while here when really I just want treat everything after this as just a value, or basically basically what I need is a separator and say that, if I just do this, it's a bit ambiguous because from Haskell's standpoint, it looks like I'm passing less than or equal to 30, then drop while as a separate argument, and less than 20 as another argument, then x is another argument. So one way of disambiguating that is putting parentheses around it. Haskell also lets you do this $sign operator, which basically, it's a function like anything else, but basically it just sort of separates everything else, and it's equivalent to saying that putting parentheses around this. So you might see me do that for just because I'm used to it. I'll try to be a little bit less.
Injecting a little PHP into the.
Nominally, yes. Basically, it's not like anything else we could look like. We could look at it. It is the function application operator, you could call it. So it takes a function from A to B, takes an A, gives me back a B, right? So it basically calls this function. But basically, the sort of operator precedence is set such that it effectively does this. It effectively says. It disambiguates, this is the function, everything before it's the function, everything after it's the argument.
Right.
So thanks to the associativity of the operator, that's sort of how that works.
That's pretty cool.
Let's see, can I define my own symbol functions? Yes, you absolutely can. You can define operators in Haskell like everything else. There's nothing too crazy about that. So let's say I could define, let's call it, what's something that's not? Someone says the arrow pipes and then a greater than sign. We could define that operator in Haskell like this, just like any other function, actually. The only difference is we have to have parentheses around it so that it knows that this is an operator, basically. So I can do this and say A, B, and it returns, I don't know, A times B or something. So it works like the same thing as the multiplication operator. And then from there on, I can do A like this. Oh, right, sorry, I didn't define these variables. 1, 2. And it'll do the same thing. It does 1 times 2.
Pretty fancy. Andre said it's interesting how functional programming looks brilliant and exciting right up to the point where you get to monads.
Yeah, OK, so monads. For those who are familiar with Haskell or have seen Haskell written about online, the sort of meme is that monads are this crazy hard thing, and that that's this crazy thing that Haskell has that makes it impossible to learn. And there are like a billion monad tutorials. Like, this is what monads are. Monads are like a burrito, which are all kind of ridiculous. Monads are not that crazy. I don't think I'll get to covering them, at least outside how to use them. I might get to using some common monads, because like if you want to do input-output operations, you will be using a monad in Haskell, but you don't have to know what a monad is in order to use it. I think that there's sort of this hype around monads, in my opinion, that they're made out to be harder than they are. They're different than something that you may have seen before, and they're rooted in a mathematical concept, but like they don't have to be as hard as it's sort of like you don't have to understand group theory to do arithmetic. For those that don't know, group theory is basically a generalization of arithmetic that you might study in a college math course. You don't need to be familiar with group theory in order to do arithmetic, and it's sort of a similar thing. You don't need to be familiar with category theory to use monads. If you really want to understand them at a very basic level, then maybe maybe you want to learn some of the sort of category theory stuff. But I think monads are really made out to be more difficult than they are, and they're really useful. In fact, I miss them a lot in other languages when I'm writing code in other languages. I hope we'll at least get to talk about. I'll at least get to show some monads, if not really talk about what monads are.
The definition I tell my friends, which makes them less confused, is it's just a way to linearly describe nested computation and unpack and repack values in the same context.
That's an interesting definition. I would say that functional programming, it's really about like I mentioned this earlier, but it's really about describing what a computation is rather than how to do the computation. It's sort of up to the compiler to figure out how to do the computation. It's like in what order things sort of go in, and the fact that it's called functional programming is useful too in the idea that functions in a functional programming language are true mathematical functions. What I mean by that is that the arguments exactly determine the return value, right? So the return value, the only thing the return value depends on is on the input arguments. So we can see like in like a C program where that wouldn't be the case, right? So like int main. Actually, I won't define main. I'll just define a function. It foo int x, something like this. Right, so there are a couple ways that we can write a function where the output doesn't depend solely on the arguments. One is to define a global variable, int y equals 7, and I'm going to return. I'm going to increment y, and then return x plus y or something like this.
This is what's called a closure too, as well, right?
Closure?
Closure, CLOSURE, where you sort of enclose the surrounding variable, the environment, the variables. So you have access to lexically defined variables outside the scope of the function.
Nominally in C, this isn't what it would be called.
I guess because usually those are lambda functions too.
Yes.
That are closures.
But yeah, there is a closure idea going on here in that the global scope is available inside the local function. But so here's an example. For example, I could call foo with the same argument. I could call foo 1, and it would get me a different result every time I call foo 1. Right? Every time I call foo on 1, it would give me a 1 increased every time I called it. And so this function doesn't depend on its arguments, or doesn't depend solely on its arguments. Another example would be something like, I'm not going to write out the whole getting input in C, because we don't have the CS50 library. No, we do have the CS50 library, but otherwise it's a little bit more of a thing. But suppose I did have a function that got an integer from input, so I'll use the CS50's getInt function. So if I said int x equals sorry, I've already defined x. Int x equals getInt. Right, now I don't even have a global variable, but I'm getting a function from input. And now if I return like x plus y or something like this, this function again doesn't depend solely on its argument. There's something else sort of influencing here, and this is something that Haskell prohibits. So that is a really powerful notion that I think really defines purely functional programming is the fact the technical word for it is referential transparency. The idea that the output of a function is solely determined by the input to the function. And so if you want some kind of state, then you pass that in as an argument as well. I suppose one reason why that's super important is because it makes proving the correctness of an algorithm really easy, right? So if I really want to prove that my algorithm is correct, if I want to, even if it's an informal proof, I'm just trying to show my boss that the program that I wrote is right. It's much easier to reason about programs when the output is solely determined by the input, which is something that I really like. Okay, back to Haskell.
Someone said, Sutheron said, I have a Haskell exam in 3 days, and I see this live stream, so they pop up in my feed. Haha.
Hey, you're welcome to, if you want to jump in and teach it, you're welcome to. I have not taken a class solely on Haskell, but I have done a fair amount of small projects, and as I mentioned earlier, some research that involved Haskell.
Haven't taken any classes, but wrote the GHC compiler. Yeah.
I have not written the GHC compiler. I wrote a compiler. It's certainly not. GHC is easily. That's like the most big brain. There's like GCC, the C compiler is impressive. GHC is like on a whole nother level. It's ridiculously impressive the stuff they can do in GHC. I'm constantly impressed by that. Okay, so what else? Well, I suppose one other kind of nice feature of Haskell that I did sort of want to point out is if you're familiar with list comprehensions in Python, you can do the same thing in Haskell, which is really a sort of a nice way of encapsulating, of writing code more concisely. So if I wanted to say, I mentioned earlier that I had 1 to 10, right? This gives me a list from 1 to 10. But like, suppose I don't know, I wanted like all the right triangles, all of the side lengths of valid right triangles, things that conform to a squared plus b squared equals c squared. I could write that sort of in terms of list comprehension. The way that I do that in Haskell is I'd say, well, ultimately what I'm going to be getting back from this are pairs x, y, and z, and then where am I getting these x, y, and z's from? So this will be this vertical bar is like the I suppose it's a bit like the for in Python. It's sort of the equivalent of for in Python list comprehensions. Or if you're familiar with like just set builder notation from mathematics, it's exactly what the vertical bar is in set builder notation.
Like where?
Yeah, such that where. Yeah. So basically this is the triple x, y, and z such that or where. Where am I getting x from? I'm getting x from say I'll say I want the first 10 integers. I'll say I'm getting y from the first 10 integers. And I'll say I'm getting z from the first 10 integers. And then I can also add a constraint here, right? So I've said where I'm getting these x, y's, and z's from, but I want these to follow the Pythagoras' theorem, right? Where x squared plus y squared equals z squared. I can just do x squared plus y squared equals z squared, right? And then now this gives me all of the right triangles with side lengths at most 10.
That's so cool and such an elegant way of describing the problem too.
Yeah, so certainly, and certainly sort of the idea of Haskell, as I mentioned, there's no for loops, right? There's no for loops, there's no while loops. The way that you sort of write the equivalent of iteration in Haskell is with things like map, is by building lists of things and then iterating over them. And so that's sort of the so a sort of comfort with lists is important. Now let's talk a bit about how we, so I mentioned that Haskell is sort of, I mentioned that Haskell sort of favors, and functional programming in general, favors recursion over iteration. In fact, as I mentioned, there's no for loops, no while loops in Haskell. So how can we build those sorts of things? And I think maybe one introductory example. Let's just talk about writing a sum function, right? So a function that takes a list of integers, finds the sum of all of them. And there's lots of ways to write this. I'm going to write it initially using sort of only the basics, and then maybe as we go on, we can improve the implementation a little bit. First thing that I should do is probably specify the type of what sum is. I'm going to call it sum prime because sum is the sum function is actually a function in Haskell, and I don't want to override it. I'll now specify the type. What should the type of this be? Well, it should take a list of. We'll make it not generic initially. We'll say it's going to take a list of ints, and it's going to return an int, right? So int, a list of ints to int, right? And Haskell does have type inference, so actually I could leave this off. Generally, it's considered good practice to write out the types for your functions, but Haskell will let you leave it off. Okay, so sum prime. Now I define what the function actually does, right? So it's going to take. I said it's going to take a list of x's, like this. And how do we write this recursively? Well, how do we think about sum recursively? Usually when you think about solving a problem recursively, you think about how to break it down into smaller problems, right? How can I turn the problem of taking the sum of the entire list into a problem of taking the sum over some smaller portion of the list? Well, for taking some of the list, it's really, in order to get the sum, I should take the first element and add it to the sum of the rest of the list, right? Here's my sort of initial approach, and this is definitely not necessarily idiomatic Haskell, and we'll sort of get to how we can improve this in a bit. But okay, well, the first thing I should probably check is my base cases. Is the list empty, right? And so as it turns out, the function for taking the list as empty in Haskell is called null, N-U-L-L. And so I'll first do if null x's. And then the sort of syntax for if conditions in Haskell is if then else. So I'll do if this is true, then I want to take the first element of x's. In Haskell, we get the first element of a list by a function called head. So I'll say head x's. And then I'll call my sum function recursively. I'm actually doing this a little bit backwards. I said if null x's, then I should be first handling the case where the then condition should be the case where x is actually empty. So I apologize for that. If x is actually empty, what I want to return then is just 0, right? If null x's, then this should evaluate to 0. Otherwise, the list isn't empty, so I can take the first element of it using this head function, and then I'll just I'll add the first element to the result of sum, calling sum on the rest of x's. The function in Haskell for getting all but the first element is called tail, right? So head gets the first element, tail gets everything else. So I'll say sum tail x's. This is not necessarily idiomatic Haskell. This is probably a poor way to write it in Haskell, but this is just sort of an initial approach.
This is how I would see it in like Clojure or Lisp or something.
Yes, yeah. So Haskell does have if conditions. One weird thing about Haskell if conditions is that you need an else condition. You can't just have a then. This is because if is an expression in Haskell. It needs to yield a value, right? So regardless of whether null x's is true, regardless of whether x's is empty, this condition needs to return a value. So I need both a then and an else.
This actually looks very similar to Python too.
Yes,
the if then else in one line.
Exactly. Yeah. So this nominally works. But there are some ways that we can improve it. And here's one example that I want to show. Well, first I suppose let's test if it works. And someone asked, I saw in the chat, how do we compile a function with GHC, so not using the interpreter? Well, first I'll show you how to use the interpreter. So we can load up this function in the interpreter by calling GHCI and then just the name of the file. So I call it test.hs, and it will load up the function. It'll load up the file, and so now I have access to that sum prime function. So sum prime, let's say 1, 2, 3, and it gives me the sum of 6, which is correct. Okay, so how do I actually compile it and get an executable instead of loading it up in the interpreter? Well, it's the same thing, just with GHC instead of GHCI. So GHC test.hs. Excuse me, I don't have a main function. Let me say main. This is the sort of empty main function, and this is a bit weird syntax, but we'll maybe talk about it in a little bit. Don't worry about this just yet. I need a main function though to compile it, and so if I do that, then so that I don't necessarily introduce the syntax, I'll have it do. I'll have it print out sum 1, 2, 3. And so that we're defining our main function to just print out the sum of the list 1, 2, 3. And so now if I do this, oh no, didn't like that. Why not like that? Oh, because it expects this to be a string, so I need print. Put stir line expects a string, print expects something else. So I need print there. I apologize. Okay, good. And then if I ls, I have an executable called test, which prints 6. So that's how you compile it versus how you load it up in the interpreter. So we loaded this up in the interpreter, and we noticed that it worked there as well. How can we improve this? One way is to use something in Haskell called pattern matching. Before I get into that, I should introduce an operator that I didn't talk about before, which is, I didn't really talk about list operations probably as much as I should have. So we saw this function 1, 2, 3, 4. How would I add an element to this list? The operator in Haskell for doing that is the colon. So the way I prepend an element to the list is I say, if I want to say add 0 to the beginning of this list, I would say 0 colon the list 1, 2, 3, 4. So this adds 0 to the beginning of the list. What's really cool is we can do something called pattern matching here to improve how this function sort of looks. We can sort of separate out the cases between when it's empty and when it has elements, and I'll show that here. So now let's write our new sum function. So I'll call it sum double prime, and we're going to get a lot of primes here. And similarly, it's int to int. How can I improve this? Well, first, let's just say, let's say I do tell it, I do have the empty list. What Haskell can do is it does something called pattern matching. So if the first argument is the empty list, which is denoted by open bracket, square bracket, then I just want you to return 0. So I'm saying sum double prime, if I run sum double prime, which I haven't defined in the interpreter yet, but with the empty list, I want it to return to me 0. Right? So this is sort of a sort of nice intuitive syntax. Now, what about the other case? Right? So what if I call it with anything else? And this is where we can use that sort of colon operator to do what's called pattern matching in Haskell. So what I can do is I can write this, x colon x's. What does that mean? Well, remember that when I write when I write 0 colon 1 2 3 4, right? What that is saying, this is equal to, in some respects, 0 1 2 3 4, right? So I can when I write x colon x's, this colon operator is sort of working in reverse. I'm saying, I can represent 0, 1, 2, 3, 4 as 0 colon 1, 2, 3, 4, right? And so if I do it this way, then x will be whatever the first element of the list is, and xs will be the remainder of the list, right? So I'm sort of it's called pattern matching because this is the pattern I wanted to follow, x colon x's, and if this pattern matches correctly, then we'll be in this branch of the sum double prime. Does that make sense?
Yeah, roughly.
Okay, so then I can sort of write the same thing that I did before, right? X plus sum double prime x's, right? I don't have to use head and tail again because I've already sort of separated x and x's. And so and this ends up being all I need. So if I save this and I open up in the interpreter, this should work. So if I call it on the empty list, it gives me back 0. If I call it on 1, right, it gives me 1. And here's sort of what happened here. When I called sum with list of 1, well, it first looked, does it match this case? Does it match sum double prime? Is the argument the empty list? It's not, so it skipped this case. Then it tried to pattern match this, and what it found out, it sort of realized that, well, hey, 1 is the same thing as 1 colon the empty list. Right? These are sort of the same thing. And so it assigned x to 1 and assigned x's to the empty list. And it called 1 plus sum double prime on the empty list. Right? Sum double prime on the empty list is 0. 1 plus 0 is 1. So that's kind of how it works. Someone says, can't you just call load on the file again to reload it? Yeah, you totally can. I forgot. I forgot about that. That's a good point. If you want to reload a file that you've already loaded, you can do colon L or colon load. And that actually, wait, you have to do colon load in the name of the file. So you have to do test.hs. And that would work. I think is reload or reload would load the same thing. Someone says, so it doesn't overload the definition of sum double prime. I mean, you can look at it as overloading, I suppose, if you want. You're sort of separating it out into two cases. You're saying, if it's the empty list, do this. Otherwise, do this. Haskell will prevent you from having sort of overlapping patterns. Like if I tried to do sum double prime empty list equals 1, Haskell will just say that's not a valid function. It'll say, if I reload, it'll say pattern match is redundant.
Right.
So
two things can't be the same thing, two of the same use case can't evaluate to different values.
Yes. Actually, I'm surprised that isn't actually. Oh, it's just a warning. It's not a compiler. I think it probably actually just takes the latter definition.
Oh, it just overwrites it. Okay.
Yeah, but it does warn you about it.
I'm kind of surprised that it would even do that. I'm surprised it wouldn't just abort altogether because of the pure functional ambiguity sort of.
Yeah, I suppose. I'm a little bit surprised at that, but I suppose it just takes the first definition, it looks like. But it does warn you about it at the very least.
Okay.
You shouldn't have had this in the first place.
Taking the first one makes more sense to me. Yeah.
Yes, yeah. So that is, and I suppose that actually makes sense. The sort of notion that equals means sum double prime with the empty list is defined to be 0. Anything after it's, I didn't lie when I said it the first time.
Yeah, that seems a lot more cogent.
Yes, absolutely. Now, someone says, Cosmic Luis is posting another way of doing it using reduce or fold. That is very true, and in fact, where I'm going to next. So, I appreciate the prelude, just a bit of a Haskell pun, if you're familiar with it. Haha. Okay. So, we should talk about fold. In other languages, it's called reduce. This is a little bit strange.
I think mathematically, it generally seems to be called fold.
Yes, yeah.
Reduced seems like it's kind of a more, I guess, more of a mainstream sort of renaming of it.
Yes, yeah, exactly. So reduce is what it's called. Like in Python calls it reduce. JavaScript calls it reduce. Other languages, some other languages will call it. Well, no, I take that back. That's not the same thing. Yeah, reduce is somewhat common mathematically. Fold is probably the better idea. There is in Haskell something called fold L versus fold R. That just basically means where it starts on the list. Does it start from the left side of the list? Does it start from the right side of the list, respectively? I'm just going to be using fold L. There's times when you'd want to use one or the other, but I'm just going to be using fold L here. Let's look at what fold L is, right? So what does it do? Okay, foldable T, that's immediately confusing. The one thing that I'm going to say here is that we can just replace this with the list. The list type meets the foldable sort of requirement here. So we can replace this with, if we just specialize it to lists here, it's B to A to B to B to list of A to list of B. So getting rid of the T here, fold is technically a little bit more generic than that. We don't need to worry about that currently. Okay, so what does this do? It seems a little bit weird, right? All right, so initially, we could read this as a function from that takes a B, returns a function from A to B, like we said earlier. But it's more helpful sometimes to think about it as this is a function that takes a B, it takes an A, gives you back a B. Right? It's a function that takes two arguments, a B and an A, gives you back a B. Then I give it a B, I give it a list of A, and it gives me a list of B. Here's what it does. So this B to A to B function is something that basically what fold does is it iterates over a list and accumulates a particular and accumulates a value. Every time for each element on the list, it calls this function, this B to A to B, with the value that it's already accumulated, that it's been accumulating, the next value in the list, and then it returns the new accumulated value that'll be used for the next element. This may seem a little bit high level, a bit strange, but I will. It'll make more sense once I say write sum in terms of fold. The B here is just the initial value, the initial value of B before we've called this function, and then we have the list of A that we're going to be folding over, and we're going to get back a list of B at the end. Seems like that's quite a lot, but. Here's sort of the idea. So if I want to write sum, how can I write it sort of in terms of a fold? Well, the thing that I'm going to be accumulating as I iterate over the list is going to be the sort of running total, the sum of all the elements up to that point, right? So I could write fold L, and I'm going to be writing it in a slightly more verbose than I need to here. And again, we'll sort of talk about why maybe we could do this a little bit differently in a bit, but. I'm going to be using, excuse me, sorry. Boo. We'll talk about why, how I could be a little bit better about this in a bit. But basically, okay, so what do I want to do when I fold over this list? Well, this first function, I'm going to use Haskell's lambda syntax. This is similar to using lambda in Python. I could do /. A, B, this just means I'm taking a function. I'll do B, A, so that it maps, it works with the types over there. This just means I'm defining a sort of anonymous function that takes two arguments. So, and really, I just want to add them up, right? So B is sort of the value that I've been accumulating as I've been folding over this list, and A is just the next, the current value of the list, right? So I'm just adding them together and returning the result.
So this B plus A maps to this B here, right? This, oh, I'm sorry.
Oh, sorry, that was my fault.
So this B to A, rather these two parameters here map to these two here, right?
Basically, yes.
And then this B plus A is actually this B return,
yes.
Right?
Yeah. Okay. So I'm being a little bit weird about notation here. In this context, the B and A were types. In this context, they're actually variables. I'm just naming them in a similar way to sort of make it clear what they correspond to. So we're going to say B plus A. The initial, what's the initial value of my sum going to be? Well, it's going to be 0, right? Before I've read any elements, the running sum is 0. And then I just give it a list of 1, 2, 3, 4, right? And I get 10. And that's sort of what I expect. It gives me back a list of B at the end. In this instance, A and B are actually the same type. They're all ints, so that's totally fine. But how can I write this even maybe a little bit better? Well, let's remember that this seems this part seems a little bit weird. This anonymous function that I sort of wrote. All I'm doing is adding up two numbers, but there's already a function that does that, right? Just the plus the plus operator does that, right?
So could you just write plus?
Exactly.
A,
yes.
B?
I can just write plus.
Oh, all right, okay.
Right,
because it takes the parameters implicitly.
Yes.
Okay.
So just this works totally fine.
Right, that's how you would do it in like Lisp that I'm aware of.
Yes.
Too, yeah.
So So folds are something that are used when you want to iterate over a value, when you want to iterate over a list, and sort of keep a running total in some respect, right? So here's another example where I might want to use fold. Let's say I wanted to count the number of even numbers in a list, something like that, right? So I'll call count even, which sounds like the Count from Sesame Street's cousin.
Yeah. Count even.
Yeah. So we want to count the number of even numbers in a list. Okay, how do we do that? Well, the first thing we're going to do is it's going to take an argument initially. Well, it'll take an argument, the list of numbers that we actually want to count the number of even numbers in it. Now, count even x's. How are we going to count the number of even numbers? Well, the first thing that we're going to pass to fold is a function. And the reason why we're using fold here, again, is because you want to use fold whenever you're iterating over a list and you want to accumulate something. You want to accumulate something as you're iterating over the list. In this case, we want to keep a running total of the number of even numbers. Okay, so how do we do that? The first thing that we do is say that so we're going to define an anonymous function again. We'll call it ba again. B is the value that we're accumulating. A is the next value of the list. So the value that we've been accumulating, remember so far, the kind of idea here, the value that we've been accumulating is the number of even numbers, right? So really we sort of want to add 1 to this number if the current value is even, right? So how do we do that? Well, if A is even, right? So we can say if A mod 2, I'll do if mod A2. So mod is a function just like anything else. It just returns A mod 2.
Do you have to write an arrow here to specify that?
Oh, yes, you do. Thank you for catching my syntax error. If mod A2 equals 0, so this means the number's even. If a number modulo 2 is 0, then it's even. This is a way of checking if a number's even. So if it is in fact even, then what we want to return is b plus 1, right?
Okay.
Alternatively, if it's not even, we would just want to return b, right? The number of even numbers didn't change since we found an odd number. Okay, great. So that's our function. What's the initial value going to be? How many numbers even numbers have we counted so far before we started counting?
0.
0. Yeah. And then we just give it the list of numbers, right? So say 2, 4, 5.
You can do 1.10 as well, right?
You do 1.10, yeah. So how many even numbers are there between 1 and 10?
5, yeah.
Sorry. I should say x's because this is a function that's taking a parameter.
Right.
So
okay.
now I'll call count
even with the list of
on 1.10, and it'll tell me 5, which makes sense.
So
right?
any iteration can just be accomplished using folds, essentially.
Yep, fold, map. The other one that's common is filter, which is something is a function to only keep certain elements of a list if they evaluate some predicate.
Couldn't you use filter within a reduce, within your reduce expression here, or your reduce function?
Yeah, well, you could absolutely compose folding and filtering together. Yeah, here's an alternative way to write the same thing using filter, which is it's a great idea. So filter, let's look at what type it is. It takes an A, gives back a so it takes a function that goes from A to bool, right? So I give it an element of the list, and it tells me, and this function will tell me, should I keep it in the list or not? And then it just gives me, I give it a list of A, and it gives me back the filtered list of A. So for example, if I wanted to say, a really kind of silly example would be like, I don't know, equals 4 to 1, 2, 3, 4. Right. Obviously, only one of these elements this function is only going to return true for one of these elements, so it only keeps that. But an alternative way to do the same count even thing is let's filter out all the odd numbers, right?
So you can do mod 2 equals 0, right?
Yes. So I'll do I'll say for the eligible list,
function, right?
Yeah. So x and say mod x2 equals 1, right? So equals 0. So this will filter out all of the elements for which this function returns false, which is odd numbers. We can see that that's true, and then I can just count the length of this list, right? And so, oh boy, I'm actually forgetting what the oh shoot, what's length? I think it's length. The length of all of this. Yeah, it does the same thing. So the length is just a function that, given a list, gives you the length of that list. So I've accomplished the same thing using a filter in this instance.
Adam had a couple of interesting questions. He seems a little bit skeptical. He says, I don't see how any of this can be used for larger programs. Seems useful for small problems, but nothing else. Mm-hmm. And then at the bottom was saying, it seems like it solves no problems, but creates problems. Seems like an interesting but useless concept. What do you have to say about that?
I think you're wrong. So here's a couple of reasons for that. The fact that it can't be used for large problems is demonstrably false. the GHC compiler, that the Haskell compiler is written in Haskell. That is a huge project. I've worked on projects of substantial size written in Haskell, and moreover, I mean, JavaScript is more and more adopting a functional style, and that's used all the time. So it is true that right now I'm sort of showing just the very basic, simple things that you can do in Haskell. I'm not showing you how to write a compiler in Haskell. But I would say that the notion that it solves no problems is definitely not true. From the standpoint of it helps you write provably correct algorithms. It helps you prove the correctness of your algorithms. It's really useful in concurrent scenarios, which is huge right now. Distributed programming, functional programming is really helpful from there. Exactly, it compiles itself a problem it created. All right, man. You could write a C compiler in Haskell too. Can it compile another language? Absolutely. There's nothing specific. In fact, compiling Haskell is I would guess, is pretty significantly more complicated than compiling a language like C.
Adam, I would look at John Carmack. Since I know you're into games, John Carmack actually rewrote Wolfenstein 3D in Haskell and had a talk about it. So if you go on YouTube and do some research into that, you'll see he had some thoughts about it. I think in the end, he ultimately said that it didn't really solve any new problems, but that it was definitely achievable. So you could, I think you can theoretically write anything amongst most Turing-complete languages anyway. It doesn't really matter.
Certainly, yeah. So it's certainly the case that any program that you can write in any other language, you can write in Haskell, for the simple reason that Haskell is Turing-complete. That's not really super the point. And I'm not sure whether I'd recommend Haskell for like game development. So it's unsurprising to me that it's not as helpful there. But so I can tell you the research that I worked on. I can tell you the research that I worked on writing a compiler for homomorphic encryption, which is this really neat new sort of thing in cryptography right now. This sort of hot new topic. That was something we probably only could have done in Haskell. Okay, so. Let's move on to maybe defining some data structures and seeing what that might look like.
Cool.
All right. So how do we define a new data structure in Haskell? Haskell has what's called the data keyword. So data in this instance, it just looks like this, and we can define. Let's start with something simple like a list, or actually let's even start with the sort of ultimate simple data structure, the one that every object-oriented course starts off with. Let's define a person. Right? What does a person have? Right? So there are a couple ways to sort of specify how you define this. One way is we'll just say that a person, is it's someone who has an age. It's someone who has an age and a name. Let's start there. So that's going to be a string, and that's going to be an int. Right, it's got a name. He's got a name and an age. All right, so if we do that, let's go ahead and reload our file here. I can now write. First, I can see what the type of person is. This defined a constructor for person. It's something given a string, give me an int, gives you back a person. So I can say person, Colton, and how old are you?
28.
If you want to reveal that on stream, I don't know.
Just turned.
Okay.
People did an awesome happy birthday thing for me
Oh,
actually
wow,
on stream.
that's
It was really cool.
So let y equals person Colton 28, and now there you are. You're y now. You're set to y. Unfortunately, this isn't super helpful. For one reason, if I try to like print out y and show it what this person looks like in the interpreter, it says no instance for show person arising from use of print.
So I'm guessing you have to write a function, a specific function that the print statement expects.
Yeah. So here's one way that we could like the initial way that if we wanted to display it, we could have to write a function on our own, like something like I don't know, show person. It takes a person with a name and an age, right? So this is that same pattern matching idea before, where I am sort of extracting out the name and the age as parameters to this person, and I say, I'll write, let's see, name is years old.
So plus plus being the concatenation, string concatenation operator.
Yes. So if I do something like this, I can reload it. Reload. Oh, oops. Okay, and now I could write show person on. Actually, I'll have to redefine Colton again. Show person y, and it does this. I had too many spaces there. Oops. But that's. I forgot to put age. I'm silly. All right. if I now reload, oh no, it didn't like that. Oh, age is a number, I apologize. So there's a function called show, which turns things into strings. So that's what I will do here, show age. Turns it into a string so that I can concatenate it with the other strings. So that should work now, hopefully. Oh, right, I have to redefine y again, so reload the module. OK, there you go. Colton is 28 years old.
Nice.
We got that working. That's not really ideal. It would kind of, it would really be unfortunate if every single if every single program or every single type that I'd find, like ints, floats, all these things, had to have different functions to turn them into strings so I could display them on the console. How do I do that? Well, so one way is to, how can I avoid that? One way is to use what Haskell calls type classes, and this is a really powerful thing that a lot of some other languages have adopted. They're similar to JavaScript interface or Java interfaces. They're similar to traits in Rust. Basically, it's a different way of doing generic programming, where instead of generic programming being done by inheritance, so like in an inherited language, you can imagine maybe this inherits from some class of showable types, some class of types that can be converted into strings, or something like that. And so then you can call like a show method on any objects that derive from that class. How can I do this? How can I do this even a little bit nicer? Well, or how can I do that here? Well, instead, what the Haskell standard library defines is something that would look like this: class show s. So where show is the type that's showable, right. Where show goes from s to string. So I'm using class here. Notice that, so one thing here is that in Haskell, class refers to type classes. Classes mean something that's a little bit different than things in other languages, than what class means in other languages. It doesn't mean like class in other languages would be more like data up here, where it defines a data type. That's not the case here. What it means here is this is basically an interface. Basically, this is an interface that other objects can implement, and then I can write functions that say I can take any type that implements show. So how would I implement show for person? Well, I'm going to delete this declaration since it's already defined in the standard library. But I say instance show person, right? And this sort of mirrors the syntax before, where I had class show s, where s was just a stand-in for anything. So in this case, I'm specifically I'm saying I want to create an instance of show for the person object or the person type. And now I just define what show should look like, right? So now I can copy the same thing here. And in fact, since I've already written show person, I will just define them to be the same thing. So now, what did this get me, right? This got me that now I can just, now I can, let's create that person, and then do y, and now, so now I can just print it out in the interpreter. The interpreter implicitly will call show on the result of any expression that I type, and turn it into a string so it can display to me. And that's exactly what's being done here, which is really pretty neat. Someone in the chat, Scytheron, showed a slightly different way of doing this that's a little bit nicer, and said, I might be wrong, but can't you do something like data person equals person string int deriving show? And you absolutely can. So as it turns out, this would be pretty annoying to define. This would be pretty annoying to define show for all the classes that you write. You might want to do it if you need something specific. What Haskell can actually do for you is for certain of these commonly used type classes, it can automatically derive an instance for those classes so that you don't have to do it yourself. So if I want to do that here, it'll look at the exact string that it'll turn into will be different than the show person that I wrote, but I'll show it here anyway. So I can write deriving show. So basically I'm telling the Haskell compiler that I don't want to write the show method for this. You do it instead. And then I could have reloaded that. Now, this is different than the show instance I wrote before, but it just lists out the name of the type and then the two parameters right there. So basically what I did here was just say, hey Haskell, hey GHC, derive this for me. I don't want to do it. And for certain type classes, for the type classes for which GCC knows how to do that, you can derive them. Another example of an instance that you could derive would be equality, right? So right now, even if I had, say, oh geez, sorry, I'm not used to Macs. So let's see.
That doc, I probably should have just disabled the doc at the bottom because it's come up a bunch of times.
Yeah. So let's see. Let's say let z equals, and I'm going to define it the same way. Okay, we're waiting for buffering again. It's unfortunate.
Gives a nice little pause, you know.
Yeah.
That's good stuff.
Person Colton 28 again. Okay, and you might think that, well, these things are equal, so I should probably be able to do y equals z, and that should give me true. What it says is no instance for EQ person arising from use of double equals. And this is because if we look at the type for double equals, it says that I take any types for which that have implemented the equality type class.
It's kind of like an interface.
Yes, exactly.
Yeah.
That's exactly what it is. And so EQ happens to be another one that that the Haskell compiler can just derive for you. I could write it manually myself and say instance person or EQ person,
where name is equal to name and age is
exactly.
equal to age, but it's smart enough to know that that's
It's smart enough to figure that's probably what I want. If I wanted something slightly different, I could do it differently here. But now if I add EQ to the list of things that I want it to derive, then I can do I can redefine my y and z again. Let y equals this, let z equals this, and then compare them, and it'll say true. So that's probably pretty neat.
I do like that. That's pretty clean.
Yeah, it's something that definitely is quite nice. Okay, let's do something that's maybe a little bit more complicated. One thing that's really useful in Haskell is suppose that I wanted to write a division function, right? And the reason why I'm pointing at division here, Haskell of course already has a division operator, but division is unique amongst some of the other mathematical operations insofar as it can fail, right? Anything divided by 0 is a failure. There's no way for multiplication to fail. There's no way for addition to fail, but division can fail. And so, how would what if I wanted to write a safer division operator that didn't involve floating point exceptions when I divide by 0? If I do that in Haskell currently, if I do 4 over 0, it'll say infinity, which isn't really true. The 4 over 0 isn't in fact, it isn't truly infinity. But how could I sort of encapsulate the idea of writing an operation that would fail? Well, let's try to do that ourselves, right? So other languages will call this an optional type. Haskell has a type like this defined, but I'm going to basically define a new one here. Haskell calls it maybe, although since it's already defined in Haskell, and I don't want to overwrite their definition, I think that would probably be a compiler error. I'm just going to put an apostrophe after it just to disambiguate and say this is my version of maybe. Okay, so what is a maybe? Well, this is basically I sort of want to encapsulate the idea that there can either be a value here or there's no result, right? This computation either resulted in a value or it resulted in no computations. In like C and C++, the way that you have to do this is either if you happen to be returning a pointer, null pointer sort of serves this purpose of having no value. But if you're not returning a pointer, then basically you got to like pass in a flag by reference or something like that. That's not that's not super ideal. Let's do that here. So first of all, let's make this maybe type generic, right? So I can say that it's either going to be an int or something else, but let's make it so this maybe type could represent any type. In that instance, I do it the same way that I did it for functions earlier, where I just say I put this lowercase a, and it's just going to stand in for any type. And so maybe a, it's either going to be one of two things. It's either going to be a value or it's going to be nothing at all. How do I encapsulate the idea? Well, if it's nothing, or excuse me, well, if it is some sort of value, in that case, I'm going to call that case just, right? It's just this value. This is what Haskell happens to call it, and I'll do just prime again to avoid colliding with Haskell's names. It will wrap just this value a. Now, suppose on the other instance, it might be nothing at all, in which case I'll just say nothing. And notice this doesn't take an additional type parameter because this is just a sentinel value. I'm saying this is nothing. This vertical bar here means you can really think of it as or. This maybe prime a is either going to be a just prime a or it's going to be a nothing. Let's see what that would look like. Let's see how we can implement our division operator in terms of that. Let's go ahead and write it here. So we'll call it safe divide or something like that. And this is going to take, let's say, 2 integers as input. Obviously, we could define it for floats and be a little bit more generic. Let's just initially say we're going to take integers, int to int. And it's going to return a maybe int, right? This computation maybe has a value. Maybe prime int, right? Maybe there's going to be a value at the end. Okay, so how would I do this? Well, it's going to take an x and a y. I'll call those the two parameters that this function is going to take. And well, really, let's consider the sort of special case where there's no value, and that's when y is 0, right? I can't divide x by 0. So let's consider this first case first. So in safe divide, x 0 means when I'm trying to divide x by 0, what should this be? It should just be nothing. Nothing prime, because I'm trying to avoid these collisions with Haskell. So there's no result. In the case that I'm dividing by 0, there's no result. What if I am going to divide by, if I'm not dividing by 0, so if y is anything else, in that instance, then we still need it to be of type maybe prime, so I need this just prime thing, and it's just going to be x over y. Right, so now when I use safe divide here, it's going to, well, let's go ahead and see what it does. And just to make sure I can print the results out here, I'm going to go ahead and do a deriving show so that I don't have to implement the show instance for maybe. It'll just do it for me. So let's go ahead and reload. Oh, yikes. No instance for, okay. I'll make these floats. It doesn't like it when I'll make these floats.
Divide ints by ints.
Yeah, because that might not be an integral value. That's fine.
Right.
So maybe prime float. That's fair. I should have considered that.
Someone said that they are reminded of Donald Knuth by you.
Oh, well, wow. I will definitely take that as a compliment. Donald Knuth is really, he's an incredible lecturer. He's also, I have his Art of the Computer Programming books, and they're really fantastic. So I guess thank you. All right, so we want to reload this. So we reload this, and let's see if it sort of does what we expect it to. So if I do safe divide, oh Jesus.
Because in VS Code on there, I should have disabled the doc. I apologize.
I use Linux on my laptop. I'm not super used to the Macs. All right, so safe divide 4 and let's say 5. Right, it gives me 0.8. That's exactly what I expect. That's nice. What about if I try to divide 4 by 0? It gives me nothing. Right. Someone in the chat asked Donald Knuth, or Donald who? So Donald Knuth is a professor at Stanford. He's a really, like a foundational guy in algorithms and in computer science generally. I highly recommend. He has a really great series of books called The Art of Computer Programming, which are fantastic.
Very math focused, though.
Very math focused. Yeah. But so they do. Like they give you a sort of, at least initially, the first book covers a lot of the math stuff. It's like a series of 4 books. I think he's still writing more. But it does give you sort of a mathematical foundation of programming and that kind of stuff. So I'm a big fan of it. Okay, so this is really great, right? We sort of encapsulated this idea of having sort of optional values, which, in my opinion, so this is an example of something that I miss in languages like C and C++. There are so many times when I'm writing a computation that might fail, and I have no way of sort of encapsulating that in the type system in some way. I basically have to, like, you sort of have to pass maybe the function returns a bool and returns the result. It takes its result as like a pointer and sets that pointer or something like that. That is definitely not ideal. I would much rather have the ability to say, hey, I might have a value here, I might not. And so this is something that I definitely miss in other languages. The Haskell equivalent is just called the exact same thing, just minus the apostrophe. So no different there. Okay. So now let's think about what other instances we might want to sort of think about deriving for this. So EQ probably makes sense, right? And as it turns out, I probably don't have to implement this. I can probably just say EQ. And if I do that, everything sort of just works, right? So I can do just prime 2 equals just prime 3. That would be false. Just prime 2 equals just prime 2 is true. Just prime 2 equals nothing prime. Right, and that's false. So we didn't have to do that ourselves. All right, so I do want to get into, I'm probably not going to get into monads, but I do want to get into some of the really powerful abstractions that Haskell has that sort of get close to the sort of notion of monads and those sorts of things. So let's define let's say a tree structure. Right? So, or actually, let's define a linked list. Right? A linked list is pretty easy. So once again, a linked list, we can define it really the same way. So I'll call it a list, and it's going to be generic. It's going to be a list of some type A. Let's say we're going to say that's equal to. So a list has sort of two states it can be in, right? It's either empty, or the value of a list is going to be a pointer, or is going to be an element of the list, and then a pointer sort of to the next element, right? That's sort of how a linked list works. And we can encapsulate the same idea here. So I'll say the first case where we actually have an element of A. Well, it's gonna have an element of A. And then it's also going to have, the other thing that this element is going to have is a list, right? The remaining list. So I'll say list A, right? So this lm is parameterized by sort of two values. It has two members of it, the element and the rest of the list. Alternatively, if we don't have any more list here, if we're at the very end of the list, the last element should probably point to something like nil is something what it's sometimes called. Basically, the end of the list, right? And so, how does this sort of the syntax might seem a little bit strange, but let's sort of play around with the syntax in the interpreter and see why this sort of does encapsulate the notion of a list. And so, I will go ahead and derive show so that I can show it in the interpreter. Okay, so let's say how would I write 1, 2, 3, 4 in this sort of new list idea? Well. I know that anytime that I'm writing a list, I'm either going to have to write lm or nil, depending on whether it's some element of the list or the end of the list. Okay, so the first element of this list, if I'm writing 1, 2, 3, 4, right? Just so I remember what list I'm trying to write. So 1, 2, 3, 4. So let's do lm 1, right? That's the first element. Then what follows should be the rest of the list, right? Okay. Well, what's the rest of the list? It's going to be lm2, followed by the rest of the list. What's the rest of the list? lm3, followed by what's the rest of the list? lm4, followed by nil. I think that's enough. No. Great. Excuse me. And so now that I've defined this now that I've defined this new kind of list, I can have this sort of notion of a list of many elements, right? This has a lot of other sort of syntactic things, but you can see encoded in here I have 1, 2, 3, 4, and then the end of the list. Okay, but like now I probably want some of the other abstractions that we might have for like the other functions that are implemented for regular Haskell lists, right?
I'm guessing we could like fold. Use
fold, use map. Those are all things that I definitely want to include. So just as an initial example, head in Haskell. Head was that function that, given a list, would give me back the first element, right?
Right.
Okay. So how would I write that? That's pretty easy. Let's call head list. It's going to take a list. Right, so and I can use excuse me. I'll specify the type first. So I'll take a list of A and give me back just an A. Right, just to give me back the first element of the list. And actually, well, here's something that's maybe a bit one consideration, which is what should I do if the list is empty? Right? What should I do if there are no elements of the list? How can I take the first element of the list? Right? This is something that really, ideally, should sometimes be able to fail. And so the way that the normal head function in this in Haskell does this is it throws an exception, which is really not ideal. I actually don't like the fact that that head in Haskell just sort of throws an exception instead of returning an optional value like it probably should. But we can do that here. There's no reason we have to do that same thing. So let's have our head list return a maybe A, right? So basically this is going to return the first element of the list if it's there, or nothing at all. Okay, how do we do that? Well, once again, there's sort of two cases, right? So if our list is an lm, right, that means it's a non-empty list, and so I can write lm, the first element we'll call x, and then the rest of the list we'll call x's, although it doesn't really matter what I call the rest of the list. In this case, I just want head list to be equal to x, right, the first element. Alternatively, if it's, excuse me, I want to call it just x, because I'm returning a maybe A. Alternatively, head list, if it's nil, should just be nothing, right? There are no elements. So does this work? Let's reload. Okay, head list. I'll redefine y as I head it up here. So head list y should give me 1, just 1, great. Head list with the empty list should give me nothing, fantastic. That's exactly what I wanted. Okay, great. So we've at least done this. But now, we might want to do map, right? So map is really useful for Map is really useful, as we saw earlier, for lists. Let's define the same thing for this new kind of list, this new linked list that we've created. So let's say map list is going to take a list of A. Excuse me, it's going to take a function from A to B. It's going to take a list of A, and it's going to give me back a list of B, right? So it's sort of the same idea from before. Okay, so once again, we sort of want to separate into two cases. What should map list do if the list is empty? So we'll call the function f. But if the list is empty, then probably we just return nil, right? Same thing. If we try to map a function over the empty list, it just gives back the empty list. Okay, so map list f of what if we actually do have values in the list? So lm x x's again. Well, then what we should do is we should return the same. We should return a non-empty list. So we have lm here, and then we want to evaluate f on x, right? So the whole thing here is that we're trying to evaluate this function on every element of the list. So we have lm f x. Now, what about the rest of it? What about the rest of the list? Well, this is where the sort of notion of recursion comes in. I've already called f on the first element of x. Now I need to call f on the rest of the elements of x, the rest of the elements of the list, and that's exactly what that's sort of the recursive subproblem here. So I can just call map list f on x's on the rest of the list, and this will give and this will work exactly as I expect. So if I go back, Jesus. Go ahead and reload this. We'll say map list of nil. Excuse me, I need to give it a function. Map list of, let's say, +1 on nil should give me nil. Great, awesome. And now map list over, say, lm1, lm2 nil. Right, so this is a function. This is a list that just contains 1 and then 2. This gives me back the mapped version of this list.
1, 2, and then 3. Nice.
Yeah. But okay, so this map structure is kind of nice, right? Like this is something that you could imagine almost any container that you'd write. If I write a set, if I write a hash table, if I write a tree, the ability to sort of map a function to all of the elements in that list is something that seems kind of useful, right? It seems like something that I would want to be able to sort of write generically for any kind of container. Well, if I want to write it generically for any kind of container, that sort of suggests the idea of that type class thing before, right? This sort of defining an interface,
yeah.
An interface for all the mappable objects, right? Well, how do we do that? We can do that. Let's say class mappable, and then the thing that's going to be mappable, we'll call it A, where. So what should a mappable class, in order for a class to be mappable, what should it have? Well, it should have some sort of map function, right? So we'll call it map with a prime on it, so as not to conflict with Haskell's regular map on lists. And this should be, well, what should the type of map prime should be? It should take an A to B. No, sorry, I'll call this C. So it should take an A to B. It should turn a CA into a CB, right? Where C is just generic. It could be a list. It could be a list that we defined. It could be Haskell's list. But this is we're sort of generically defining this mappable notion over any possible container, right? So C is standing in for container here. Okay, so well, we have two containers that we know about so far. We have Haskell's lists and the lists we just defined. Let's define mappable for these. Let's say instance mappable A, list of A, right? So for any list of A, where let's say map prime. Well, it's just gonna be able to map, right? For the regular Haskell list, they've already written a function for it, so awesome. We don't really have to do anything. Similarly, instance mappable, let's say list of A. And in this instance, again, we've already written a sort of map-like function down here for it, so we can just put that here. Alternatively, we could define it here similarly. But since I've already written it, I'll just put it here. And now what this means is I can write functions that sort of generically, that are generic to the container type. So here's what I mean by that. If I wanted to write a function that adds 1 to every element of any container, right? What I could write is, let's say add 1, and we'll say I'm going to take any mappable type, C, any mappable container, this will take a C int to a C int, right? I'm just going to add 1 to every element of this container. Right? I can do this, and since I have this mappable class, I can do this generically for both lists, the list that we defined, and Haskell's lists. Right? And all it's going to be is add1 equals map prime plus 1. Right, and this sort of this is a really powerful idea. In fact, it's so powerful that Haskell already thought of this. So we defined this mappable class, but as it turns out, this is something that Haskell has too. It has a class defined in it called functor. And functor is just a mathy word for exactly what this is. So in Haskell, functor would be defined as exactly as we defined this before, functor C, where, and instead of calling it map prime, it calls it f map for functor map. But it looks like this: A to B to CA to CB. And Haskell already has this. So you can immediately write functions that are generic to the type of container when you want to do these map-like operations. And Haskell has lots of these for lots of different scenarios, which is super powerful.
It's actually pretty handy.
Yeah.
I've always heard the word functor and not really understood what it meant. But to be fair, I do need to dive into this a bit more and do some more reading.
So unfortunately, like in C++, like in that world, they use functor to mean something different. In C++, they use functor, which I don't like this use of the word, but in C++, a functor is basically an object that, any class that implements the operator parentheses. So really any class that you can call like a function.
Interesting. Yeah, that's completely different.
In a Haskell and mathematical sense, a functor is just something you can map over.
The word functor in that context actually makes more sense to me.
Yeah.
Because I'm like, oh, basically makes it callable as a function. It's a functor, you know?
Yeah.
Obviously, right?
But admittedly, some of the terminology around Haskell, it comes from the people who wrote Haskell were mathematicians mostly. I mean, mathematicians and programmers, obviously. And so, like a lot of the words come from math, so functor is something that comes from category theory in this instance.
Catamorphism being another one. That's
yes.
the only one that I happen to know.
Exactly, catamorphism, anamorphism, all these fun math terms. But in Haskell, what a functor means is what's a functor? A functor is something that I can map over. Something, it's basically a container that I can map over. And monad is really no different. It's just it's another one of these things with a slightly different interface. It's not something that I can map over. It is a little bit more complicated, but not really anything too crazy. I think that's all. That's all I want to go to in terms of functors and things. Do you have any questions?
We're getting the word that we actually have to go to the particular event on campus here today. So this actually be a good part because we just kind of tied this the whole functor concept kind of up neatly. This would be a good point, I think, to maybe take some questions, a couple questions, and then try and wrap up the stream. So it was pretty cool. I like Haskell. I like how elegant you can express very sort of mathematical relationships, and then they just work. It's kind of a very elegant, beautiful thing.
Yeah, absolutely. So someone says, so as Puppet 4411 says, so as a complete beginner to functional programming, what should my mental model be when trying to solve a problem in a functional way? And that is an excellent question. So really, there's two things that I think you want to keep in mind when solving things functionally. First of all, I'm touching my mic. Oops, sorry about that. First of all, sorry about that. You want to as I've said a few times, functional programming is really about recursion. Recursion is how you do most things, and so you probably want to at least get a little bit comfortable with the idea of recursion. And so that's something that you can practice in any language. But the notion of breaking problems down into smaller problems is something that it comes up a lot in functional programming. The other way is thinking about composition is really an important part of functional programming. So I have the composition operator in Haskell takes something. I know how to turn B's into C's, and I know how to turn A's into B's. So therefore, I know how to turn A's into C's. Right, and you can express a lot of things in terms of composition. I mean, any sequence of steps you can represent in that way, and that is something that's super useful in functional programming. And Haskell specifically, and other strongly typed languages, you also want to think about how can I encode as much as I can in the type system. That is a super powerful thing, and it helps you write very correct code. You got any good sources for learning Haskell? Yes, I plugged this at the beginning of the stream. But in case you weren't here, Learn You Haskell is fantastic, and I took some of my examples from them. This is actually how I got my introduction to Haskell. Highly recommended. It goes through a lot of the various syntax in Haskell. It includes monads. It includes all this stuff, and all in a really, I think, accessible way with lots of visuals. And Learn You Haskell will probably do a much better job than I have during this stream. So highly recommended.
Yeah, awesome. And also thanks to JS Coder, Kuros Kira, Gucci God, and Mohammed Noor. I don't think I shouted those followers out previously. Asli, what are you working on now using Haskell?
So I'm continuing development currently with Alchemy, the thing I talked about earlier. I can pull it up on GitHub. I don't know how useful that'll be, but CPiker, this username is not me. This is my research advisor. But this is the project that I was working on, a language and compiler for homomorphic encryption made easy. And this still needs
easy with the Y.
Easy with a
nice.
Y to make the acronym work. As a super short sort of explanation, homomorphic encryption is this really cool thing in modern cryptography where you can evaluate functions on encrypted data. And what that means is, like, I could encrypt, say I want you to do some work for me. I could encrypt some data. I can send my encrypted data to you. You could do work on that data, get an encrypted result, and send it back to me. You have no idea what you just computed, but I still get a meaningful result out of it, right? So like, you can imagine this for like like 23andMe, those services where you send your genetic information and they send you back information about your heritage or whatever. Like, you might not actually want to be sharing your information with them, like your genetic information. Like, that's super private. And so what you could do using homomorphic encryption is encrypt your genetic information, send it to 23andMe. They'd do an analysis but get an encrypted result at the end. They'd never have access to your actual genetic information and send it back to you. And so it's fairly recent. Like, the first plausible construction was in 2009, and it's very, very interesting. Okay, so there's a question about, if I'm not good in recursive thinking, can I still go into functional programming and learn more about the recursive way of thinking? Absolutely, yeah. So functional programming will sort of, in essence, to some extent, force you into that model, into that mindset, which is good. Like, the way that you get good at the recursive way of thinking is by writing recursive things, is by trying to write things recursively, by reading other solutions of things written recursively. So, like, absolutely, the functional programming would be a great way, and Haskell would be a great way to sort of get that in mind. So the next one is what is from JS Coder? What is the benefit of learning Haskell? I would say even if you one thing that I should have emphasized a little bit more is that learning Haskell or learning functional programming in general, but Haskell specifically, isn't just useful if you're it isn't just useful in order to write functional code. Like, it's not just learning Haskell has benefits outside of the ability to write Haskell. It is the sort of functional style of things is commonly recognized as a good style to write code in. Again, removing global state, removing mutability when you can. It's really good for sort of concurrency and these sorts of things. So I think that learning Haskell and learning Rust and languages like that have made me a better programmer, even when I'm writing Python or C++. So I really think that's fantastic. Are you a Harvard student? I am not. I'm a senior at the University of Michigan. I'll be a PhD student next semester, but I don't know where yet. Let's see. A language and compiler for homomorphic encryption made easy. That title's a whole lot of note for me. Yeah, I admit it's a bit of a backronym, I suppose. But I think I did not come up with the title, although I wish I had. I kind of like it personally.
We'll take this last question before we wrap up. Scala or Python for functional programming from BubbleDead12.
So admittedly, I don't have tons of experience with Scala. So I can only speak to Haskell in that respect. Haskell. What I think about is really good about Haskell is the type system is still, I think, stronger than Scala's, to my knowledge, which again means that it more pushes you towards the idea that if the code compiles, it's probably correct. And then also, the Scala has always been in a bit of a weird spot for me because it's kind of built on top of Java, and it just seems like it's always just seemed a little bit, I don't know, a little weird to me.
Hey, get careful. Clojure is also built on the JVM.
Well. And Haskell also pushes you towards I don't know about Scala, but Haskell does push you towards a purely functional approach, which I think is useful. It's useful to even just as a way to make you a better programmer, it's useful to sort of push you in that direction.
And then to Meow Haha's point, not related to functional programming, is it possible to talk about how to approach reading source code? And Adam actually plugged it. We did some code review streams, so definitely check those out. We have to wrap now, a little bit rushed today. Apologize, but thank you so much, Chad, for the awesome stream on functional programming. It was really cool. I got to learn a few new things, and actually the functor demonstration at the end, that was actually really cool. I really liked that one. Excited to actually kind of now I want to dig into the book and read a little bit more myself and do some more understanding. But cool, thanks so much, everybody. Next week we have Nick and then Doug. We'll be doing a genetic algorithm stream on Friday. The schedule will be updated, and then we're sort of figuring out a time slot for Nick. But tune in next week. Until then, enjoy your weekend. Thank you all very much for tuning in today. This was CS50 on Twitch with Chad Sharp and Functional Programming with Haskell. We will see you all next time. Bye-bye.